I think fine. Sure. So let's have your first slide and then, yes, I think this will be nice. Okay. Then we will wait for a couple of minutes. We have 10 more minutes and then we will start. Yeah, I think our IGS President, Dr. Anil, also joined. Good afternoon.
Yeah, very good afternoon. Very good afternoon. Yeah.
Good afternoon, Doctor.
Yeah, good afternoon, Anil Yunatcı. It's a pleasure to have you to talk to on this particular topic today.
Thank you for your initiative, Professor.
Yeah, we are yet to start. We have few minutes, so that's why you are not able to listen, I think. So good afternoon. We will start in few minutes. We have 6 more minutes. So Dr. Yunatcı, how should I pronounce you? I'm sorry. Am I rightly pronouncing or anything?
You're essentially pronouncing it perfectly, Professor. That's how it should be. Thank you very much.
Yeah. I was a little bit, concerned about that.
Almost better than the natives, I would say.
So your name is a bit similar to our IGS president's first name.
Oh, yeah. It was Professor Chopra when I first realized this coincidence. Back when I was an undergraduate student, we used to just use his dynamics of structure books. So that's the first time I came up with the similarity.
Yeah, very interestingly, we are from different part of the globe, but we carry the first name.
It's good, no? We are starting his lecture also first.
Yeah.
Maybe we can start once Andrew join. I'm just waiting because of this time differences, different time zones.
Yeah, I think still it's only 3:26, so you have time. So
Yes, I have 4 more minutes.
Yeah.
So how are your preparations going for 2026?
Yeah, we just started. We made that first brochure, right? And which has been circulated in the recent ARC also to all the participants. And so anyway, me and Anil, we are working. We just started because it's still time, 3 years more. Maybe it may start in a full swing from 24 June. Right now, we are actually started, talking to people and trying to identify and speakers, etc. So anyway, I will take your support also. I think Dr. Andrew is here. Good afternoon. Good morning. Dr. Andrew?
Sorry. Apologies, I was on mute. Good afternoon, good evening, good morning.
Good morning.
Good
Good
night,
morning,
wherever you
Anil.
are in the world. It's good to see so many people.
So we'll start. We have a couple of minutes, 2 minutes more.
Good morning or good afternoon to everybody.
Yeah, good morning. Good morning.
This is
Good afternoon. Good afternoon, Mr. Antash.
Good afternoon. Good afternoon. How are you, Dr. Anil? Everything is good?
Oh, we're
Yeah,
doing well.
everything good.
Thank you for the invitation. I'm very happy to join you. Actually, this subject is very important, very interesting, and has a big potential here in Saudi Arabia.
So along with our IGS president, Dr. Anil Joseph, our honorary secretary also just joined. Dr.
Good morning.
APC.
Good afternoon.
Good morning, good afternoon to India, and good morning to you.
So it's 3:30. We'll start. Anyway, that is the recording. So it will be uploaded. So shall we start, Dr. Andrew, Dr. Anil?
Okay, yes, thank you.
Yeah, let's go.
Okay. Yeah, thank you so much. So good afternoon, everyone. Good morning to Europe and other parts of the country world. So it's my warm welcome to this inaugural lecture of our much anticipated, lecture series on field monitoring in geomechanics as a part of TC 220 of ISSMGE. So I try to coordinate this series, and I should thank first of all Dr. Andrew for giving the full support in doing this. He's our chairman. And I'm truly delighted to see all of you here. And this is going to be recorded also, and extend my sincere gratitude to your participation. So the field monitoring in geomechanics, which is like very crucial in construction and infrastructure developments that's happening, the rapid growth, especially countries like India, where it is exponentially increasing. So this topic is something very, very crucial to understand, share our knowledge. So to also see the challenges that are there from the diverse geological conditions, like, we have like such a diversity in geological and geotechnical setup, and rapid increase in the urbanization and sustainability concerns, that's very much crucial in decision making of the major infrastructure projects. So through this lecture series, the aim is to bridge the knowledge gap by hosting distinguished experts who will share their insights, experiences, and cutting-edge approaches for in-field monitoring, especially. So we have our first speaker, Dr. Anil Yunatcı. So I welcome you, Dr. Anil, for kindly accepting this first lecture. So with this welcoming words, I would like to request Dr. Anil Joseph, IGS President, just to, because he's also a member TC 220 along with me. So just to add few words.
Yeah, very good morning, Andrew Ridley, the chairman of TC 220, and the speaker of the Anil Yunatcı. It's a great pleasure to have this curtain raiser for our ISSMGE 2026. First of all, I would like to once again thank Andrew for giving the opportunity. It was last time in September where we had that bidding, and India won the opportunity to host ISSMGE 2026. I would like to thank my co-member in TC 220, Nilima Satyam, who is taking the initiative and is fully energized to welcome all of you to India in 2026 in Indore. And as a part, this curtain series is happening, and we want to spread the TC 2020 series also. So this will be a continuous process. And we have a very apt topic today, harnessing the gems in instrumentation and monitoring. All eager to listen to that. And I would also acknowledge the presence of our Honorary Secretary, Dr. A.P. Singh, and different personalities from the TC 220 who have joined in for this. Let's all be ears for this wonderful lecture from Anil Yunatcı, and look forward for a great time together. And thank you, Andrew, we will be in touch with each other to make this TC 220 in Cochin, in Indore, a grand success, in India, a grand success. And I remember the one fantastic way you have done that in London last time. Thank you very much for the opportunity, Nilima.
Yeah, thank you so much, Dr. Anil Joseph. So shall I request Dr. Andrew Ridley, who is the chair for TC 220 remarks?
Okay, thank you, Nilima, and thank you, Anil, for your very kind words. I don't want to take up too much time. Just to give a little bit of background, the TC 220 is a technical committee of the International Society of Soil Mechanics and Geotechnical Engineering. We set it up in 2019, and the aims are to disseminate knowledge in the field of monitoring and instrumentation. Since then, we've successfully, as Anil mentioned, we've successfully run a conference in London almost exactly a year ago. We were all there. And this initiative to run an international series of lectures came out of the last full TC committee meeting that was held in May this year in Rome. And I think it demonstrates the value of running these committee meetings, because these ideas spring up. I think this is an excellent idea, and I hope that it will have great longevity. I should thank the Indian Geotechnical Society and Nilima in particular for taking up the role of running this series of lectures, and also to Anil for his support to host the first lecture. So thank you very much for that. I will come back at the end and give a few notices on events that are coming up. But for now, I'll hand back to Nilima and to Anil for the lecture. Thank you very much.
Thank you so much, Dr. Andrew. And so we'd like to start our lecture. So I take it as my honor to introduce our first speaker, Dr. Anil Yunatcı. So he is a geotechnical engineer. He's working for Geodesic Limited, and he's also representing a nominated member of TC220 of ISSMGE. And actually, he has gained a lot of experience, research experience in the field of geotechnical earthquake engineering, more specifically to seismic hazard assessment before joining the industry as a full-time design engineer. And he also has an experience in site characterization, in situ testing, as well as geotechnical monitoring. He received bachelor's degree in civil engineering in 1999 from Gazi University in Turkey, and then obtained his master's and PhD in geotechnical engineering from Middle East Technical University, Turkey in 2010. He is currently in charge of organizing and running numerous customized in-phase geomechanical modeling courses and workshop events internationally. And he has done extensive work on field monitoring. So with this brief introduction, I'd like to welcome again Dr. Anil Yunatcı for this first lecture series on field monitoring in geomechanics of TC220 of ISSMGE. Thank you so much for accepting, and we can have your lecture for 45 minutes, then we can follow up with some question and answers for 15 minutes. And your lecture is in recording mode. Thank you.
Sure. Thanks for the invitation, Professor Satyam, Professor Anil, and Andrew for organizing this. It is my pleasure to just to say a few words on the first of the lecture series of the technical committee. So when the invitation came up, I just sat for a few minutes before answering on what could I talk. I thought that the most versatile thing to just disseminate on behalf of the committee was to just reflect the missions and objectives of the committee to the engineering society. So this covers a wide range of participants all over the globe with different levels of experience and different levels of involvement into the projects as procurement departments, technical managers, field engineers, and researchers. So diving directly into technically intensive discussion during the first lecture did not seem to be the way. I don't know how you will just accept it, but this is going to be my style for the next few minutes. So by the way, English is not my native language, so apologies in advance if I make any mistakes or interruptions. I will just try to be as clear as possible and try to respect my time, which I do have some difficulties sometimes. So in basic sense, the mission of TC220 committee is just to build a bridge between the real behavior of any geotechnical structure and the predicted behavior. What we refer to by the predicted behavior is that it can be calculated or estimated using some empirical, semi-empirical, or analytical calculations, or it can be just fully dependent on some more rigorous methods of numerical modeling in the finite element, or more advanced methods of numerical analysis. So the basic thing is what we assume initially is not always reflecting what is happening in the field. Just take an example of a deep excavation project and try to have an idea of the possible failure modes of an anchored pile wall. So the real behavior versus predicted behavior and the possible modes of failure should be clearly foreseen or should be considered in your stability calculations during your conceptual design or your finalized design. However, we have a range of diverse uncertainties which arise from uncertainty due to mechanical characterization of materials. This may not be the correct expression. However, I think it simply just expresses its purpose. The uncertainty due to mechanical characterization may arise from spatial coverage, strength characterization, constitutive behavior, or any other type of both aleatory and epistemic, aleatory variability and epistemic uncertainty while characterizing the phenomenon. There are also uncertainty and changes in external and internal loads, such as pore pressures, or you may consider pore pressures as internal or external, depending on how you characterize and define it, as well as external loads. There are uncertainties due to performance and mobilized capacities of man-made support elements. So what we basically put and define in our good-looking finite element analysis in terms of the pre-stress value of a tendon may not always work out or almost never works out in the way that we considered initially. There will be changes in characteristics of geomaterials and structural members over service life due to deterioration of the structural elements and its interaction with the natural materials, as well as some long-term possible changes in the characteristics of the geomaterials themselves. So the solution will be just finding an engineering way to fill the gap through observational data. Continuing to the objectives, you may reach the committee through its website, dedicated website, through ISSMGE main site, and maybe Andrew will just spend more time on discussing about these, so I will skip them very quickly, or you may just simply log on to field-monitoring.org to learn more and see how you can contribute. We are trying to cover the civil industry, the mining industry, define or monitor geological hazards such as rockfalls and toppling failures, work in the energy sector, renewable sector, keep an eye on the existing infrastructure as well as the newly built infrastructure, both in different time spans. So what I refer to this by saying the time span is basically we may monitor a structure while it has been undergoing the first construction stage or during its service life. Historical structures, similar approach, industrial, and many others I may have just skipped to emphasize here. So a very brief note on the upcoming events and activities. So the instrumentation monitoring will be discussed early in October in Salzburg, Austria. There will be a specific session reserved for instrumentation monitoring in the ISRM Congress. So BGA, British Geotechnical Association, has announced a seminar, a meeting, half-day meeting at Institute of Civil Engineers. Here you can just note down the access link and have more information about that. Next year in Barcelona, and similarly in the 18th European Conference on Soil Mechanics and Geotechnical Engineering, which is to take place in Lisbon, Portugal. We'll be discussing more and having dedicated sessions on instrumentation and monitoring and how we can just make it progress better. And last but not the least, one other fixed event, which we have already mentioned, the largest dedicated event, International Symposium on Field Monitoring in Geomechanics, will be held in India in 2026. So before just proceeding to the more technical parts, I think we can just take a moment of silence and respect and tribute to the legends and pioneers in this field. I am pretty much sure that I had just a few seconds to emphasize or talk about only a few names. There are many other respected ladies and gentlemen, researchers and practitioners in the field who have just devoted their lives to build the bridge between advanced numerical, geotechnical analysis and field observations and bring it into practice. So with due respect, what we have learned and are still learning from the previous generations are still the crucial items that we should be considering, regardless of the tools and the advanced methods that are available to us today, thanks to the advancing technology. But the basic principles are staying the same, and they are becoming more and more evident and pronounceable. So to begin with some fundamental definitions. Sometimes this vocabulary is mistaken and used in conjunction of the other. Sometimes we say we're measuring something. Sometimes we're pronouncing we are monitoring a parameter, and we're making data acquisition. So I would believe it's just emphasizing that they are slightly different in terms of complexity and the perspective we are taking in terms of their inclusion into instrumentation and monitoring. To start with the most basic one, okay, you're using some data acquisition tools and methods to make measurements. They may be digital or manual, traditional, it doesn't matter. What you basically have is data which is unreducted, unprocessed, unvalidated if it's been recorded in the correct range or not. Then you are simply trying to turn it in this to a piece of knowledge. And that's where the concept of monitoring is coming. So monitoring is basically covering, in my sense, all the aspects of it, plus the data interpretation and telling people in the most basic sense, what is happening to my structure, what has happened to my structure, and what is likely to happen to my structure. So the last question is not always easily answered. The motivation behind geotechnical instrumentation, we are after just the performance assessment of new or existing geostructures. In the most basic sense, we need to define their potential failure modes. We need to just verify if they are performing okay with in regards to the assumptions we have made before the construction stage. So it is not the only sole structure that we're trying to build or monitor, but there are some adjacent structures or assets which are potentially affected by the behavior of our structure. So it's not us always. Let's not be selfish in this sense, because any consequence will directly affect what will happen to the nearby structure. So the motivation is just to bring a working sense, a working framework, which is undoubtedly has to be customized specifically for each project we're involved in, to optimize the solutions for all parties involved, both in the technical sense, financial sense, and the legal sense due to its possible consequences. So in terms of the budget optimization, so balancing between under-conservative and over-conservative design extremes, just one of the pluses, one of the advantages of why you should monitor a structure. So frequently encountered misinterpretations from our daily basic experience. We have heard directly from any stakeholder that this instrumentation is unnecessary, the structure is safe, instrumentation is expensive, it's hard to apply instrumentation programs, it's obstructing and decelerating my construction program. So data acquired from instrumentation programs cannot be used efficiently. They are all strictly and 100%. I have to just express it very freely that they are misinterpretations. If you just analyze the structure, analyze the phenomenon in the correct way, and propose good, efficient solutions, then instrumentation will be essentially helpful in both monitoring the performance of your structure or and prevent any legal obstructions or conflicts. I had a chance to just go through my notes during the panel I attended about 3 or 3.5 months ago in Rome. It was the 9th of the series of the international course for geotechnical and structural monitoring. And these are not my words directly. These are just jotted down words from the speakers of the panel who are just individually very experienced in their fields and have decades of experience both in just manufacturing instrumentation monitoring products, deploying them, managing large volume projects with a lot of instrumentation involved, and just taking care of the financial side of it. So we can just expand the list. However, I am sure that while I am talking, you are having a chance to just go over some of the topics. I won't take time to go over them one by one, but just select a few random ones. Okay, sensor-based data and remote sensing integration. Perhaps a decade ago, it was the discussion of should we go with sensor-based data or remote sensing, which is better? Now it's not a rivalry anymore. It's just we have realized and more successfully implementing the uses where they come together and produce greater value. Merging new technologies and conventional tools, still we have to monitor some parameters in the old style, both to be used as backup data as well as just combining new technology data with the conventional one. One of the topics that I'm very keen on is just we're paying attention as human beings to data we gather from failures or underperforming cases for piles which have settled too much, or excessive lateral deformations experienced at a deep excavation project, and we're collecting data and back analyzing it and just trying to back calibrate our numerical models and do some forensics works in case they are needed. But my perspective is just paying attention to data from well-performing or non-failure cases, processing them in the neat sense as the others, as the failure cases, and making a value out of the well-performing cases will just give us very good insight on the unbiased performance assessment of similar structures to be built or already built in similar conditions and methodologies. So processing data, extracting information, human brain and machines and coding go along the way. They go all the way in harmony. But our perspective is that although we have the nicest tools available and the methodologies to handle the ever-increasing, ever-growing number of sensor data we have in a project, they are too much in some sense to be handled manually. So the human brain is here just to process and filter any outliers, extract any useful information. Then that experienced human brain is also responsible for making a meaning out of what is available in terms of data and use it in the phenomenon of dynamic monitoring. This is, again, not my word. And to just conduct an iterative numerical model calibration process. not easy as it's said. We'll go into the details because we know how the design and the investments are realizing in the real world. So just dynamically iterating a numerical model and revising your design in a steady manner will require some amount of efforts and regulation evaluation to be effectively put into place. And that's one of the most dominant challenges of today and main topics of discussion in my point of view. Let's check my clock. Okay. This conversation or chat, let me say, was just put out for the purpose of making the newcomers to the field a little bit affiliated, familiar with the challenges, opportunities that we have in the field of instrumentation and monitoring. So to put it straight, maybe it's just better to move very quickly between some case studies and try to explain what we have learned from them or what mistakes we have made and how we could improve them better for the next time. So the thing is, my first example would be just on the basic strain monitoring of steel braces in a deep excavation project. I am aware that there are numerous papers, scientific papers written on this. I am just trying to go over a very brief explanation of the what is happening between the design officers or the procurement officers and what is really happening in the field, and how we can play a dominant and a collaborative role in just joining all these missing pieces together to reduce the question marks in everybody's mind. So when you are just installing a strain gauge in a steel casing, steel pipe section used for lateral supports in a deep excavation project, okay, only some of the challenges that you come up and you have to answer is just when you should take the zero reading, what is your true zero reading? How dominant can temperature effect may play a role on the readings you take, and where you should place those sensors. Just speaking of the zero reading, you have several options. You can just install your strain gauges at rest state, where they are lying on the ground with no bending stresses and no lateral restraints. So if they are just properly supported uniformly and they will not be restrained at both ends, then what you have is a sort of zero reading over there. So any strains on the zero reading will be indicated, will be just driven by the temperature changes, even if they are not restrained at both ends. So this is what happens when it's lying on the field waiting to be installed. And the second stage, now you just put it in the place where it should be. However, just do not make the connection. So it's somehow without the connections and the restraint, operating in a way that it is not fixed yet. However, the members are in the effect of their own self-weights. So you will have a different zero reading over there. What you're comparing should not be pears and apples. So be careful on when you're installing it and when you are reading your intermediate measurements, then just it will be very useful if you do both and try to compare, and that will help you explain what is happening in the field. Only the bending stresses are due to the self-weight of the structure. Here again, I'm not talking about any temperature changes. And I have not made any excavations yet. I have just placed the struts. Then I fix the ends of the struts, maybe include a load cell in between the reinforcement support and the elements, so that I can just do a benchmarking by measuring the loads directly or try to infer the loads on the struts because of by directly measuring the strains. So this is what happens if they are put into temperature effects when they are fixed. So the equation is basic, and let's do an extreme calculation. It's a 30-meter long hypothetical element, as I've showed, and we are just living in an extreme environment where the daytime temperatures are highly fluctuating and the change in temperature reaches up to 30 degrees Celsius. Let's see what happens hypothetically and how it is reflected into your readings. So my scenario is the temperature changes from 5 degrees Celsius to 35 degrees Celsius. I have not made any progress in the excavation. Let's see what happens. There are forces induced and the stresses. We do the basic calculation, just select the generic strut cross-section, and we are just calculating that we are about experiencing 110 tons of thermally induced extra stresses on the structural members just due to temperature fluctuation. We do not normally see this in our numerical analysis because we do not conduct numerical analysis on basis of these temperature effects. A lot of case histories showcased in the literature. One of them is taken from Osborne et al. 2023, that's access date. Here you can see that over temperature change of almost 10 degrees, the strut loads on average in 3 different strut levels goes from 1400 kilonewtons to 1800 kilonewtons. So imagine that you are not taking continuous data from your strain gauge readings. Here locally, we don't do that. We recommend that. We do not always succeed in that. It's just some temporal readings taking at each excavation interval or weekly, which is mostly requested, and we object to this. And what happens if you don't carry on a proper practice of frequent sampling by also capturing the temperature change is that you cannot just differentiate any effects of load change due to temperature and versus the excavation stages. By taking the proper readings, you may have the sensor right, you may have the sensor installed right, but if you don't have the if you haven't set up the monitoring program accordingly in the appropriate way, then what happens is that you miss those data and you were faced with questions that the strain gauges are working in an erroneous way and you are not measuring what you should be expecting. So place of installation, whether just directly along the supported sections or along the mid-span or the quarter span is another discussion. So the thing is, as you all know, you may have some load or strain concentrations, non-uniform concentrations along these members. So take an eye on where you are installing and the potential effects of installation. The number of strain gauges fitted along each cross-section. So if you use a double, hopefully if you place it in the up and down direction, then you will get the effect of the axial plus bending, because the bending will be due to the self-weight of the object and any changes onto that. So if you are just installing them facing each other along the hopefully neutral axis, then hopefully you will be just experiencing only the axial effects. If you use more, 3 or 4 strain gauges, then you have the luxury of eliminating any eccentricity related effects and see what is going on. So how you design the monitoring project and the details really matters, and the quality of the data you get. Of course, it increases the volume of the data to be processed. However, it gives you a very good knowledge at the end if you interpret it correctly. Most of the time, or just some of the time, we're facing with some difficulties as practitioners, like being faced with a bill of quantities in some procurement stages, like it's saying that not efficient information is provided. I am sure that some of you are also experiencing those issues, and this is only to be overcome by disseminating the knowledge and experiencing and bringing all people together in a common sense. I am sure this will be resolved, and we are quickly spreading and accelerating the perception, advancing the perception of instrumentation monitoring in all projects. So we're improving. If you're just faced with a simple bill of quantity, 4 strain gauges, then you begin asking more and more and more until you hopefully get a good result on what the project is aiming to monitor. And sometimes you are the one who should figure it out and propose good solutions. I have talked about the placements and what it will just bring to our measurements, but I won't just go deeper into the technical detail. One other case study. This was one of the projects that we were involved in. This is a paper mill in Turkey. It has a 2,500 tons per day capacity paper production plant. This is a finished aerial view. Back when we were involved, it was just an empty construction site. So before installing the main foundation, which was very sensitive to the settlements, we decided and we proposed to do a full-scale load test location. So instrumentation and monitoring for the purpose of quality assurance and design verification. In the most basic sense, in the most basic set of equipments and methodologies in which we can provide some useful data to check our assumptions and numerical models. The sensitive equipment was considered to carry loads ranging between 150 to 300 kilopascals, and the raft, which was ranging from 18 to 165 meters. So it's such a big plant. It was located in a very seismic area, and a series of combined pattern of drilled concrete, rigid columns, impact type, rammed aggregate piers, and GCC columns were designed for group improvement. We did some CPT tests, some borehole logging, and tried to characterize the site. I'm passing these quickly just to give you an indication that the site was properly characterized in any sense possible. And there was a very good planned, very neatly planned series of instrumentation plus quality assurance, whatever you may call it, during the intermediate stages of ground improvements. So after each stage, we still did some CPTs and seismic CPTs, as well as surface geophysical measurements, to see the effect of what has happened and what was the effect of the ground improvement process on the realized values before making a full-scale load test. A few glimpses from the field, a few glimpses from the nearby faults located 2 kilometers away, which is capable of generating large magnitude earthquakes, and the construction site. Surface geophysical measurements. A sequence plan of the instrumentation during the successive stages of ground improvement. Then we came up with a series of recommendations and verification through instrumental data on if the desired performance was achieved. We did not stop there. We were aware that the actual loading was to take place on a very large amount of area. So just by ignoring the size effects up to a certain extent, we decided to make a full-scale loading on a limited area. The design load was selected as 191 kilopascals, and the loads were applied, dead loads were applied by 3 by 3 meter. So we applied concrete blocks as dead loads reaching up to 170 tons. And we set up an instrumentation system to see if there were any consolidation settlements, which means that if the ground improvement stages were completed successfully, if the elastic settlements were the only source of settlements we would encounter, and if they were within the tolerable limits for the performance of the structure. So we saw that the site was monitored remotely, real time, by a very simple set of instruments through real-time monitoring system. And we saw that the system worked seamlessly for a period of 1 month, and 90% of the total settlement was completed within 36 hours of completion of the design basis load. So it was almost all elastic settlements. This was validated. Then the amount of settlements were used to back calculate this very simplified numerical model of the foundation, which is to be resided there. Then we updated our estimations of the subgrade modelers, both in the static sense and the dynamic sense, because there was going to be a working dynamic machinery, vibrating machinery inside an industrial site, to come up with updated estimations of some geotechnical parameters, which were then handed to the design engineer for conducting an iterative approach on the foundation performance assessment. So the thing is, as simple as it gets, we had a chance to play with multiple parameters, but this was one of the most simple cases we had. For some other problems, we have multiple parameters which are sensitive to the output, and they are nonlinearly related to each other, and which means that we have countless options to back calibrate our numerical models. So it's somehow becoming an art to back calibrate a model using field observational data, and it has always been like this. So the lessons learned from case study 2, detailed site characterization during preliminary design phase, direct assessment of design inputs for machine foundation design were put into action. And we considered that we made a small contribution to overall risk management during the lifetime of the facility due to geotechnical performance related issues, because the next stage for the investor was to just decide on, along with the third-party investors, of course, the insurance rates for the industrial site. That's where instrumentation monitoring was mainly put into action. So moving on to case study 3, don't worry, we don't have much. We're about to just wrap up. So it's about long-term monitoring of a site undergoing slope displacements, and another 3B case, which is about test fill monitoring. My complaints and conventions will be similar. That's why I intentionally selected to include these cases in under a one case study. So just a quick reminder, as almost all of you are experts here, so groundwater level measurements, we have to just define what we are measuring. So borehole water level is not always equivalent to hydrostatic pore water pressure distribution. That's why we're talking about not the borehole water levels in general during the rest of the presentation, but the piezometric levels. Numerous ways and technologies and tools to measure them. Multiple tools, vibrating wire instruments, fully grouted installation methods, Casagrande standpipe piezometers installed at different elevations. So I'm not concentrating on the tools what we have, but the output and the essence of the story. One parenthesis to be opened here. I really like this reference and work and like to refer it everywhere in any case I can. I know that this is a big project and I have just quoted the reference. If you're interested, you may have a further read here. The thing is, the astonishing thing for me here is that before the excavation began, because since this is an urban excavation, which any adverse consequence would affect all stakeholders nearby, just the project owner had to begin its instrumentation program 1 year before the excavation began to have an idea of the fluctuation of the piezometric levels nearby and have an estimation of how the pore pressures would be just distributed behind their excavation and update their numerical modeling efforts in a similar sense. This would also provide them invaluable data in terms of capturing the fluctuation of that parameter within a year due to seasonal changes or rainfalls, so that they would have a luxury of just differentiating how much of that fluctuation do experience during the construction stage was due to the construction process itself and how much of it is due to the nature of the groundwater characteristics. So I'm just skipping and closing the parentheses. You will have new, just very valuable information in just capturing on how vibrating wire piezometer, fully grouted ones are should be installed in the field. So a little bit of field experience from our side. And back to our case 3A, a failed slope site, again in an energy plant site where we were invited to monitor. The plan was set up and we had an array of portable inclinometers, steady inclinometer readings, and piezometric, multi-level piezometric readings. One thing I like this, we're still monitoring this site and it's still working over 7 or 8 years. We lost some of the inclinometer boreholes along the way, quicker than I thought, at different elevations. Good thing is we know where the deflection has occurred. The bad thing is we did not have any in-place inclinometers just to realize and the progress of the rate of deformation during the time that it was not monitored and the readings were not taken. We only had a chance to just go over there a couple of times a year, and if anything happened in between that time, we lost it. And we saw the consequence with clogged and lost inclinometer casings. Still, this gives us some data. Our regret, we could have done better in just capturing higher quality data and understanding what has happened better. So the behavior is relatively different at different parts of the site. At some sites, we have, at some boreholes, we have some clear just deformations reaching up to 20 meters over 45, 50 meters of boreholes in total. Meanwhile, the same problem was also evident in the piezometric measurements. What piezometric measurements actually deserve is continuous reading and logging. The chance is that our bad chance is that we did not have the luxury of just monitoring them at a steady pace, but we only had a chance to just monitor them once in a while. And this is just practically giving us not much information about why the deformations are being triggered, or if they are closely related with the changes in pore water pressures, because the displacements are cumulative, and once they're there, if you go 2 months later, you're able to measure it. Pore pressures are not. They're dynamic, they can dissipate, and once you miss it, and you don't have the chance to just build some good knowledge out of what you are getting. So the essence of the story is, if the monitoring program was put in the correct way, starting from scratch and procurement, and we had a chance to just persuade people that this was essential, it would have been a better consequence and just provides more insightful data for all of us. So another lesson learned. I'm skipping all these. Just a recommendation on how it should be in the most basic sense. Same problem, another case, a test field site, a ground improvement site where we have an array of multi-point extensometers, settlement plates, inclinometers, piezometers, and try to monitor the performance of a completed ground improvement at a port location. So I'm just simply showing the results of the multi-point rod extensometers. The fill was placed in stages, and between those stages, some measurements were also done. And after the maximum height was reached, again, we had a chance to monitor it for a while, just to see that the fill-induced settlements would be diminished until a certain point and would dissipate. And this is what happened with our piezometer measurements. Some of the piezometers were just located at depths where the ground was improved, and that section was supposed to be undergoing only elastic displacements only. And some of the piezometers were just located at elevations where some minor consolidation-induced settlements were expected. The same thing, our regret is that we could have just obtained more valuable data here by getting continuous, maybe hourly or bi-hourly data from the piezometers, and that would be very efficient in terms of just bridging the gap between the design assumptions and what's been observed in the field. Okay, a lot of discussions going on for the ground anchor loads, for the press stressing levels, not for the experts in this field. However, as we've told and shared, there's a great deal of necessity, a demand for disseminating our knowledge to the engineering community and the public and the investors, that we are the interpreters. We should be just playing the role as interpreters and bridging the gap between explaining what is happening in the field and what is the assumption in the design stage. Just a simple 2 rows of press-stressed anchors, a hypothetical a model that I built in a finite element space using different constitutive models. I will not go through the discussion of using the appropriate constitutive model in your modeling. However, just be aware that we are just playing with juggling between balls, having different sensitivities, and it is essential for all parties who are involved in the engineering cycle to be playing their roles in the most correct sense. So the model should be built right, the test should be, and the characterization stage should be carried out accordingly. And one ideal world that we have just reflected over here a moment ago is just we're applying some sort of a pre-stressing load over the anchors and just assuming that they are the same for that stage. Of course, they're expected to change with respect to the progressing excavation. What happens in reality that they are not. Even though that they are placed in the correct way, depending on your gripping system or the details of the manufacturer, and this value is surely to be fluctuating, and it is highly changeable at different parts of the world. You may have different experiences. You may be pronouncing different levels of uncertainty or post-locking lock of load losses than me. But in this part of the world, I am just openly demonstrating you that we are experiencing at some projects reduction up to 30% compared to design loads. What I've shown a moment ago, this is a hypothetical model. What I'm showing right here is just real field data that we're having. Here on the left column, you're seeing the design loads and pre-logging, although there was a safety margin as recommended by the standards and guidelines for increasing the pre-locking stresses, the lock of load losses are far larger than what was anticipated due to poor gripping of the components of the head system. So on the left, you see a histogram of the percent decrease of the losses in our small sample set. So it varies from 0 to 30% almost in a uniformly manner. So what happens if I carry that little piece of information back to my numerical model and see what happens? Before doing so, another parenthesis from us. I am just disregarding the improper ways of installation. I am just totally assuming that the devices are being installed properly. By the way, these two pictures are real, and we are trying to correct the practice in a way that every instrument should be installed and used in the proper way. What happens if you don't? Still in my parentheses, and thank you for your patience. I'm exceeding my time a little bit, but I'm about to wrap up. Load bearing plates on both sides of a load cell, an anchor load cell, no matter what type of anchor load cell you're using, is essential. In load cells with a fully filled cross section, the stresses are relatively distributed more homogeneously. However, you still have that problem up to a certain extent, and you can just solve it with proper use of instruments. In anchor load cells used as hollow cross sections, it is more difficult to homogenize the distribution of the surface affected by the stress. If you have a different load cell with a different geometry, you need a different configuration of supporting bearing plates to homogenize the strain and making sure that the loads are measured in the right way. What if you don't? What if you do the wrong thing, or just close your eyes to any documentation provided and by mistake, here's what you will do. If you are just trying to concentrate or concentrate loads using caps having different dimensions compared to the dimensions of your load cell, you may have readings of larger or smaller value once you just get rid of the hydraulic jack, and you're left alone with the load cell only on that. And that difference can reach up to 20% and maybe even more. And here's a controlled test environment that we made at our labs and field. We installed it in the wrong way and tried to get an estimate of how the difference was if our load cell was installed in the improper way. So although the reaction is linear, the difference has reached 26% compared to what it should be in a perfectly homogeneous distribution. Then we just verified this example using elastic finite element solutions just to showcase what happens if you use, in the proper sense, a load-bearing plate of sufficient thickness and geometry. The numerical analysis show that you can have up to 35 differences, 35% of difference, and a more proper homogeneous strain distribution along the load cell itself, so that it will measure a better value, as it should be. Just trying to replicate what is happening at our labs and doing the correct thing in the lab environment. Again, here's our deviated value when we do the incorrect installation at our lab environment. And if we correct it, now we're just getting the same value as we should be in the field. So 22% of deviation recorded at our labs, and field finding was 26%. So this is not something new, and this is not rocket science. I'm just trying to demonstrate the proper use of instrumentation products in the fields. It's not always the selection of the correct instrument, but how you install it, how you use it, and how you interpret it. Back, closing my parentheses, back to my anchor loads and my beautiful, colorful numerical model. Let's see what happens here. If I have a 10% and 20% reduction in my lock of loads in my anchor cells, what happens to my displacements? You see, the sensitivity differs with respect to the soil model, material model that you're using, and you can play around with other variables as well. It's completely nonlinear process. If you do a poor meshing, then you are more sensitive. Then what I have to say here at this sense is, if you have a field observation data, make sure that you are comparing it with a neatly tailored numerical model as much as possible, so that you will do the calibration process in a fashionable way. Same for the displacements, which are expected behind the wall. A little bit of sensitivity studies based on the real observational data. And my last words here at this phase will be the change in lock of loads. If you reflect these findings back to your numerical model and rerun the model. So my last case study, making use of observational data through multiple sources. So far, I have just emphasized on only sensor-based solutions, but we were faced with a very tough problem, which was the story was continuing for almost a quarter a century along a critical site. So they have lots of good quality data. Due to confidentiality reasons, I don't have a chance to just reflect or provide more information. But what I can say at this point is that we had a chance to work with GPS data, topographical data, some satellite-based data, as well as soil moisture sensor data, meteorological data, in conjunction with a set of piezometers, inclinometers, and associated instruments for monitoring the risk to a mine facility due to a sliding of a huge mass. What we inferred from here, thanks to the information we gathered from the instruments and being on site and just iteratively digging through every piece of information that was collected over time. Of course, we had to eliminate some of them, and that was based on judgment, and yet no machine can do it. So geotechnical engineers who are just following us here, you can be proud of yourselves. The thing is, it's a complicated mechanism consisting of deep, very deep seated slides, along with not so deep seated slides, but still reaching up to 18 meters. However, if you look at the data, there are multiple failures induced by different mechanisms and are progressing to different directions. So you have shallow slides due to seasonal rainfalls, which are just mostly controlled by the morphological features as well as the rainfall changes, and you have a deeper slide. So you can have both solutions. You will have bring a solution to the dominant problem, and you will have to understand or just leave the smaller problems to their own fate. We use all of those information to come up with a calibrated model, both in 3D and 2D in our analysis, and proposed a 4-row, a gigantic solution for slope remediation, just to slow down the progress of the moving mass. We always just combine all of these data, available data, instrumentation data, to calibrate our models, to verify or refine our failure surfaces in our cross sections and progress. So vision for the current and future industry needs. I'm fully aware that most of you are more experienced than me. So let me just put out a few words and then conclude and leave the word to you. So instrumentation monitoring is gradually becoming a standard of practice, maybe more rapidly than we consider. International standards about the general concepts are being set thanks to the efforts. Sensors are gradually becoming more affordable, however, still not budget friendly. However, they are not a big concern compared with the value they bring to the solution and the problem definitions. Coupled use of contact-based sensor data and remote sensing has become inevitable. Now we are just entering a new era where we can just collect all of them together and process accordingly. Data management software tools for sensor-based data is now becoming a standard, or has already become a standard in my point of view. The most critical missing piece, there's desperate need for trained human resource, manual and semi-automated tools, technologies, and methodologies for interpreting collected data to understand structural behavior. And that's perhaps one of the largest objectives and missions of the TC220 committee, and everyone is welcome to contribute further. As a wise man and a smart engineer said, it's all on the screen, so I will remain silent for the rest of the day. Thank you very much.
Thank you so much, Dr. Anil Yunatcı. So can we have a couple of questions from the participants? So participants, if you have anything for any kind of yourself, and then you can or raise your hand. So thank you so much. It's very wonderful lecture with different case studies starting from deep excavations to slope stability. So just to inform, this lecture series will be recorded and will be posted to all the participants also. So there is a Google form attached in the chat box. So if you want to, because this is a monthly series which has been started under TC220. So if you want to get information, regular information or updates on field monitoring in geomechanics specifically, so you please give your data, and so we'll keep posting you with all the information in the future events. So you can drop your email And so the speaker's details will also be posted along with this particular presentation. So you can directly contact Dr. Anil Yunatcı for any kind of discussions in future. So with this, I think since there are no more discussions or the questions from the participants, so thank you so much for all the active participation. And Dr. Andrew, you have anything? So participants, please fill your details in the Google form attached. Don't just post it in the chat. Kindly do that, take a minute, and then you can fill your data so that you get details from ISSMGE or TC220 or IGS also. Just for information, if you're not a member, please take the memberships. It's very important to get networked. Yeah, Google
Excuse
form,
me, can I have a question?
Yeah, please.
Yes. First of all, I am Multasem Zarzour. Dr. Amr, thank you for the wonderful presentation showing case studies. I want to ask about how the observational data facilitated how to model the site and how to find the solutions to your problem. Was it critical to have this observational data?
Sorry, I was muted, Mr. Mutasam. I would just simply answer in the way that in each of those case studies I have tried to present, they were essential in interpreting what was actually happening on the site and how the structure was behaving. So it had direct implications on the solutions we proposed for the rest of the service life of the structure. Definitely a yes.
Thank you.
So any more questions or discussions? Okay, so I assume that there's no more. So Dr. Andrew, you want to have anything to say?
Okay, thank you very much, Nilima, and thank you, Anil, for a very, very interesting opening lecture to this series. Excellent piece of work. Thank you very much. I have a few notices to give, and if I could just share my screen. It's at the moment saying I can't.
Yeah, sure. Yes, now you can.
Okay, thank you. So let me just check that I get the right one. Okay, hopefully you can see my screen now, and I'm going to just share a few brief notices with you concerning upcoming events. These two events have already been mentioned. There's an event next summer in June 2024, which will be held in Barcelona. This is a workshop which is part of the International Conference on Geotechnical and Geophysical Site Characterization. Important things to mention here are that the abstracts need to be sent to this email address that you can see on the screen, and the deadline is very quickly coming up now, which is the 30th of September. So please, if you have any abstracts on field monitoring, send them to that email address, and hopefully we'll see you in Barcelona next June. Shortly after that, there will be the 18th European Conference on Soil Mechanics and Geotechnical Engineering to be held in Lisbon. That will be in August 2024, towards the end of August, almost exactly a year away. And in fact, in 1 year today, we will be holding an in-person meeting of TC220 and a workshop. This will happen over the whole day of the Sunday, so we have a room booked for the whole day, and we will be running sessions during that day on field monitoring. So please keep an eye on the various channels so we can update you on that. It's again, it would be remiss of me not to mention the fact that the next international into that, and congratulations once again for winning the competition last September. Ways that you can keep in touch with the TC220. You can go to the International Society of Soil Mechanics and Geotechnical Engineering website, and you can visit the page there. If you follow the address there, technical committees, applications and field monitoring, it'll take you to a web page where you will find news. You can also go to our dedicated website, which is fieldmonitoring.org, and there you'll find lots of information about events that have happened, events that are happening, and just general information on field monitoring. We've recently set up a LinkedIn page, and I'd encourage you all to follow this, because this will be the quickest way of keeping up to date with what's happening in field monitoring. And if you join there, you will get notifications about any events that are happening. So, for example, today's lecture, we posted it there, and it's the quickest way of really informing people of what's going on. Our next full committee meeting will be on the 6th of September, and so TC220 members will receive an invite to that. This will be an online meeting, but it will be hopefully as many members of the TC as we can gather. Just to make you aware, if you are not a member of a technical committee, the way to join the technical committee is to approach your local geotechnical society, and they will nominate you. We don't have any say in this, unless I particularly object to somebody, but your local geotechnical society to the international society, and then I'm informed of who's a member. So, as I say, please don't write to me, because I don't have the power to appoint you, but your local society does. So hopefully I look forward to seeing you all again on the 6th of September, or those of you who are members on the 6th of September, and as many of you as possible at those events that we've highlighted. And of course, at the next international lecture in this series, news of which will be announced very soon. Thank you again to Nilima for organizing this, and to Anil for your excellent lecture. And please enjoy the rest of your day, and see you next time.
So thank you so much, Doctor.
Have a great day.
Yeah, thank you so much. And just to add it up, like, please take the membership. This is a 75th year of IGS. Dr. Anil Joseph can add a few words. There is a lot of advantage to get waive off in almost all registration fee and other things. So I think this is the right time to take the respective memberships through IGS. So can I request Dr. Anil Joseph just to have anything?
Thank you. It was indeed
President IGS.
Yeah, it was indeed a wonderful lesson, and thank you, Andrew, for the briefings, which is ISSMGE so much activity coming up, and request all to join IGS as well as ISSMGE. It's a big fraternity. It's a large family. Like Mark pointed out, it's a big family of us. Let's make sure that we are all there and contributing to the growth of our geotechnical fraternity. And all the very most. And once again, I would like to congratulate Anil Yunatcı for that wonderful lecture where everything has been covered in detail. Thanks a lot.
Thank you so much.
Thank you very much.
So with that, we are at the end of the session. So I request Kunal Gupta, who was my student, who has done a lot of work, I know, in organizing this and sending the emails, to just give a vote of thanks. Kunal.
Hello. Yes.
Kunal.
Hello, am I audible?
Kunal, you are audible.
Yeah. So respected dignitaries, esteemed colleagues, and distinguished participants, I'm Kunal Gupta, a research scholar working under the guidance of Professor Nilima Satyam in the field of landslide monitoring. I extend my sincere thanks to Dr. Anil Yunatcı for sharing his valuable insights in today's inaugural lecture. Your contribution significantly enriches our understanding of geomechanics and field monitoring. I also wish to convey my heartfelt gratitude to Mr. Andrew Ridley, the chair of ISSMGE TC220, and Mr. Paul Barton, the secretary, for their pivotal role in fostering an environment conducive to knowledge exchange among geotechnical experts. Furthermore, I would like to express my gratitude to Dr. Anil Yunatcı, the President of Indian Geotechnical Society, and Dr. A.P. Singh, the Secretary, for their continued support and for the contribution to advancement of geotechnical knowledge. A special acknowledge to Professor Nilima Satyam for her coordination of this lecture series. Your dedication and guidance have been instrumental in shaping the series and providing a platform for valuable discussion. To my fellow participants, your presence here signifies our shared commitment to advancing geotechnical understanding and solutions. Together, we hold the potential to shape a safer and more suitable future through collaborative efforts. Thank you. Thank you so much.
So thank you so much. So with this, we are closing it. Thanks for joining and have a good day. Thank you. So we are closing the session. Thank you. Thank you, Andrew. Good day. Thank you, Dr. Anil.
Thank you. Have a great day.
Yeah, thank you for wonderful lecture. Thanks.